Hi class, we are now on 3.4. We're going to look at atoms, the identity, and mass. So we're going to look at subatomic particles. And subatomic particles are protons, neutrons, and electrons. The slide should look familiar to you. The nucleus is made up of protons and neutrons, while the electrons occupy the region outside the nucleus called the electron cloud. But protons are mainly how protons determine the identity of an atom. It's the number of protons and that an atom has that determines its identity, which is what I just said. So I'm repeating myself. So let's go to the next slide. So protons, here's a periodic table. The number of protons an element has, that determines its identity. So if you look at this periodic table, this goes in atomic number and it's increasing. This number, think of this number as an address. This address is specifically for that element. And if it has that number, then that determines its identity. So if you have one proton, it is hydrogen. That's the address for hydrogen. If it has two protons, it is helium, and you can see helium's over here. If it has three, it's lithium, 4 beryllium, 5 boron, 6 carbon, and so forth. So protons, again, determine the identity of the atom. It's the number of protons an atom has that we assign that has that number of protons. We know what element that is. Hydrogen, again, 1, helium 2, lithium 3. So what defines these elements, again, I know I'm repeating myself, but this is where things start getting a little complicated as we expand out. What defines these elements is the number of protons in the nucleus. So again, these atoms, if you wanted to know which element, how many protons are with a specific element, look at the periodic table. Look at the atomic number. That is how many that element, their atoms, have in the nucleus. So atomic number and mass number. So you can go Google periodic tables, go to images, and you will see tons of periodic tables. And they're all vastly different from each other. This one only has atomic numbers. Others will show the periodic table looking like this with an atomic number and the mass number. It's very interesting. You get colors. You can get all these things that show. So I need to explain how to understand this stuff. So atomic number, the number of protons in the atom, we call it the atomic number. So when you look at a periodic table, you see the atomic numbers of the elements on here. And it goes in increasing numbers. Starts at 1, and you can see it goes all the way down to the bottom. And it's also the number of electrons in a neutral atom. What does that mean? Well, let me jump to this slide. The atoms that we're looking at right now are neutral. Protons have a positive charge, electrons have a negative charge. They have balanced number of electrons to cancel each other out, so it is a 0. So all that what we're talking about at this point means that if I'm talking about the number of protons, that means there's also the same number of electrons because we're only dealing with neutral atoms right now. So aluminum, for instance, has 13 protons. It also means it has 13 electrons, even if I'm not saying that portion of it, because we're talking about neutral atoms. So the net overall charge is 0 because 13 that's positive, 13 that are negative, they cancel each other out. Sodium, and this one you can see here, has an atomic number of 11. So when I say atomic number of 11, that means that there are 11 protons. That also means they have 11 electrons because it's at a net charge of 0. So it balances each other out. So basically it's canceling those charges out on each other. So that's what atomic number, the number of protons in an atom means. It also means the number of electrons in a neutral atom. The key being neutral, balances each other out. Mass number. Mass number is the number of protons and neutrons. So if we look at these numbers underneath, these are the mass numbers. These will help you determine, and I'll get into this later, but you add the number of neutrons up, you add the number of protons up, and that gives you the mass number. Remember, most of the mass has to do with the neutrons and protons. Electrons are very, very, very tiny compared to the masses of the neutrons and protons. So for instance, if we looked at this one here, which is nitrogen, here is the mass number, here's the atomic number. If I wanted to know how many neutrons, I could simply subtract these from each other, and that would tell me that I have 7 protons. So 14 minus 7, which is atomic number, tells me 7 neutrons. Sorry. Now, what do you do when things are rounded? They get a little complicated, but you can round them. It's kind of strange, and I try to pick ones that are very easy. so that it doesn't get weird on these, which I probably have opened something I shouldn't have right now. So we're going to come back to that. But normally you add the neutrons and the protons, and that gives you your mass number 14. Okay, so right now we're talking about neutral atoms. That means protons and number of electrons, they equal each other. All right, so before I go into isotopes, I want to give some practice to some of this stuff. Using the periodic table to fill in the atomic number of protons, and number of electrons for the following. So if I have N is nitrogen, what do I do? The first thing I do is I find it on the periodic table, and here it is, over here. So it has an atomic number of 7. So if I go up, it has 7. So I would write 7 here. That means that I also have 7 protons, and I also have 7 electrons, because we're dealing with a neutral atom. We have zinc, and zinc is Zn. So let's find zinc on here. The proton atomic number is 30. So that means that if I fill this in, my atomic number is 30. My proton number is 30, because this means the same thing. And we're dealing with a neutral atom, so it means I also have 30 electrons. And sulfur. Sulfur is over here right under oxygen, and it's 16. So by dealing with 16, I have 16, 16, and 16. So I hope this makes sense as to start breaking down and understanding the definitions of what's going on here. All right, so now I'm going to make it a little harder. Write the atomic symbols for atoms with the following subatomic particles. Now, knowing some of this information, you can identify what element you're dealing with. You have enough information. So I'm going to break this down before I show you the answers, because the answers are all on one page. What could I use? Remember I told you there's an address? The address starts with protons. If I can find the atomic number, I can figure out which element it is. So I have 8 protons, 8 electrons, and 8 neutrons. So I just got to look for 8, right? The address is 8. So this is an oxygen. So I need to write this out, but let's first identify this. This is oxygen, and I have 8 protons and 8 neutrons. So if I had to write this out, let's take a look at how we could write this out. Let's go back up a little bit. And you see that on some of these, they have, and all the periodic tables are different. I'm reading what I have, notes I've been given, and the notes are saying it's always written this way. No, it's not. Do a search on the periodic table, and you will see that the periodic tables are the information changes slightly, but the information given is always consistent. However, some things are not always written like this. Sometimes you'll get the mass up here and the atomic number underneath, and that's some of the things that it's saying, is that this is always written like this. No, it's not. But your book wants to say it is, so you'll have to go with the rules of your book. Okay, so if we have to write this out, let's go back to the page. All right. First, let's identify these. So this is oxygen. Now, what if I gave you I didn't give you this one, and I didn't give you this one. I simply gave you this right here. You could still figure out what element it is, because we are saying that it's a neutral element. If you have 17 electrons, you also have 17 protons. So once you know what the atomic number is, 17, you can go and it's chlorine. So it's chlorine, and it has 20 neutrons. And now the last one, again, what if I did the same thing? You couldn't identify it with this. This does not give you enough information. But I could give you simply this, and you would have enough information, because protons and electrons are equal. So if we go to 47, we can see 47, and that's silver. So we have all three. We identify this is oxygen, this one is chlorine, and this is silver. So when you're writing the chemical symbol out, though, there is a certain way. You write the mass number first, and then you write the atomic number underneath it, and it is on the left side. So you do the O, there's the O. 8 is underneath. Chlorine has 17, 17's here. Silver is here, 47. And then you write the mass number on top. And this is how you will write them out. If you're asked for an atomic symbol and it wants the subatomic particle information, this is how you would write it. Mass number on top, next to the upper left side of the element symbol, and then bottom left side is the atomic number. Okay, so let's take a look at isotopes. Isotopes have the same atomic number, but different mass numbers. So this means that there's atoms that have different neutrons. That's what makes these different. They have the same proton. And now remember I told you that atoms there are protons identify that element. So here's the thing, protons never change for that element. We don't mess with that. The difference is the neutrons. Some atoms have more neutrons than others, but the protons don't change. So think of this as similar to brothers and sisters. They have the still same genetic formula. There's just differences in them. So here we have one proton. This is hydrogen. We're dealing with hydrogen. Hydrogen has 3 isotopes. So we have one proton. This is the average one that we tend to use when we're discussing in chemistry. This is one proton, and this is one proton. Now the difference starts being in the neutrons. The one that we tend to use in chemistry is 0 neutrons. It means it has 1 proton and 1 electron. But deuterium has 1 neutron. The mass will be different for this one because remember, the mass consists of protons and neutrons. And then the mass will be even a larger number here because it's got 2 neutrons compared to this one, and this one doesn't have 1 at all. So these are all still hydrogen. The difference is that's how they call them isotopes, because they have different mass numbers because they have different amount of neutrons in it. And the mass will always tell you which one you're dealing with. We'll expand on that. Okay, so here I want to give an example before we start going a little bit. And I mean, most of the time to understand isotopes, you really just have to do the problems. So given the atomic symbols, determine the number of protons, neutrons, and electrons. So I've been given 3 atomic symbols here. I have to dissect number of protons, neutrons, and electrons from this information. Can I do it? Yes, I can. I'm going to cheat and just jump forward. So when you're dealing with isotopes, you're always given the number on top. You won't always be given the bottom number, but you're given the number on top. Why? Because the mass number will be different than what's on the periodic table. And that's telling you that you are dealing with an isotope. And most of the time, you're not going to just blindly know. We're usually in that section of isotopes, or something will be referred to. So if you don't see it, then it's just the average oxygen that we're using. So in this case, and I wrote these out because sometimes you have it written like this for isotopes as well. Okay, so remember mass number, this is what I was talking about. You can get the number of neutrons by subtracting the mass number from the atomic number. And sometimes you have to round because we don't deal with all these nice fancy little this. So I would round this up. You know, you have to sometimes round in order to get the whole number because we don't deal with decimals when we start dealing with things like this. Okay, so if we have an atomic number of 8, which is here, our mass number is 16, that must mean that our protons are 8. So how do we get neutrons? Very simple. We subtract 16 minus 8. It gives us a number of neutrons right here. So phosphorus, P is for phosphorus. We have an atomic number of 15. Our mass number of 31, and the mass is always more than the atomic number, so you won't get confused. The mass number is always larger than the atomic number. Number of protons is 15. Number of neutrons is 31 minus 15 gives us 16. Zinc has 65 over 30. Atomic number is 30. Mass number is 65. Number of protons is 30. And the number of neutrons is 65 minus 30 gives us 35. And if we had to write these isotopes out with a name, we write them. So there's 2 ways that you would deal with isotopes. Either you would have a chemical symbol like this, and usually the atomic number is missing. It's just the mass number on top because it won't match the periodic table mass. Or you have it written out like this. And this usually tells you the same thing. That number will match the mass number that's on top. Okay, so let's do another one. Naturally occurring carbon consists of 3 isotopes. We have carbon 12, which is how you say that. So it would match how you write it out right here. We have carbon 12, carbon 13, and carbon 14. State the number of protons, neutrons, and electrons in each of these isotopes. This is not difficult. This is very easy based on the information I've given you. It just takes time. So protons are all the same. How? Because remember, if we look here, the protons for these isotopes are all the same because we're still dealing with the same atom. So in this case, the protons are all the same. So we would look this up on the periodic table. So if we go to a periodic table here, we can see that carbon has an atomic number of 6. So here we go. And then that means that we also have, so we would have 6 across. We would also have 6 across here because the 6 positive charges cancel out the 6 negative charges. So the only difference is going to be this one here. And this is a perfect example of isotopes where nothing else is given. because you can look up the atomic number on a periodic table, and you will always, if you were in person, you would always be given a periodic table. Nobody is expected to memorize the atomic numbers and things like that. There are things that you would have to know on a periodic table, but there's some things that just you're not expected, and you will always be given a periodic table if you were in person for an exam or quiz. Okay, so these are the mass numbers. So how do we get the number of neutrons? We have the mass number minus the atomic number. So we expect the middle row to be different. So in this case, we have carbon 12 has 6 protons, 6 neutrons, and 6 electrons. That makes sense because these two cancel out. So nothing changes except for the middle one. That means that carbon 13 has 1 more neutron than carbon 12. That makes the mass heavier because remember the mass is determined by the protons and the neutrons. And carbon 14 has even 1 more than carbon 13. So how do I know that? Because remember we subtract the mass number from the proton, and that tells us how many neutrons we have. Okay, so this one's a little bit more complicated to understand, but these are things that you definitely, once you know this, you have to break it down with a little bit more thought process, but then you become comfortable with this. This isn't that difficult. Which of the pairs below are isotopes for the same element? So how would you know based on this which one you're dealing with? It's very simple. What is the one thing the isotopes have in common? The proton, the atomic number. So you're looking for a same bottom number, and that would be B. B would be the same one because these are all different, because remember I told you the address is specific to that element on the periodic table. So we're dealing with the same atom, just different neutrons for the atoms. So we have the same protons, and this one is going to be B. Same atomic number, but different masses. Now let's go to the next one. In which of the pairs below do both atoms have 8 neutrons? So now it's not saying it has to be the same atoms. It's specifically asking for atoms to have 8 neutrons. They don't have to be the same anymore. We're not dealing there. It's not asking to say that we're only dealing with hydrogens. No, we might be dealing with hydrogen and helium. It wants to know which compounds here have 8 neutrons. How do we know that? We take the mass number and we subtract it by the protons. So we would subtract this from this, 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 and this from this. And that would tell us which of these have 8 neutrons. I'm going to cheat instead of doing all the math, and I'm going to show you it's C. Same number of neutrons, but these are 2 different elements in their isotopic form, but they both have 8 neutrons to them. Okay, so I wanted to point this out. This has nothing to do with our book, but sometimes students don't understand why you guys have to study the chemistry that you do. And this is a good way of relating to life, even though it's really sad and it's a big mystery. And look at it, changed my line. I had my line here. Okay, so I watch a lot of YouTube videos and I watch a lot of videos about missing people and mysteries and unsolved cases of a bunch of stuff. I have a TV in my garage, so when I work out, that's what I watch. And this is a case of a woman who, her body was found in 1970, and they don't know who she is. And they haven't all these years. And there are tons. You could do a search on this woman. She's called the Isdal woman. And they are now trying to figure out certain things. How are they trying to figure that out? By isotope analysis. Isotope analysis right here. They can't figure out who she is. And because of it, it's just created more and more interest over the years. Why? Because when they found her body, I'm not going to go into detail, but she was badly burned. She had all the labels cut off all her clothes and shoes and everything else. Any kind of identifying mark or anything that could lead to anything was cut off. And it went to great detail to this. She had a suitcase. She gave people different names. She gave, they were able to locate that she was in a few cities, if I remember right. But always gave different names, different disguises, used fake, identification paperwork. So nobody's been able to find her, and now they're trying to identify where she grew up. Because if they can figure out where she grew up, then they can start there and expand out. How would they do that? Well, they do that by looking at isotope analysis. Because some of the isotopes, so not all atoms on a periodic table have an isotope. That means they don't all have different atoms with different neutrons. Some of these atoms, what we see on the periodic table is all they have. But there are isotopes for some atoms. And the isotopes only are found in certain areas of the world, nowhere else. So when you drink water and you are young, your teeth are still forming. Those isotopes stay in your teeth. And they can identify those isotopes by looking at her teeth. And when they can look at those isotopes, they can determine where she grew up based on those isotopes only being in specific regions of the world. And that's what they're doing. This was, I think, 3 years ago, so I really don't know now. I haven't heard anything more about this case, so they might still just be trying to figure out certain things. But this is a case of using isotope analysis to identify where somebody was born, so they can finally identify who this woman is and what was going on. Because there's all these conspiracy theories now. She was a spy. She was working for, not the CIA, but whatever is in Europe. Because this happened in Europe somewhere. I don't remember. Norway. Yeah, it's gotten bigger than, you can do searches on YouTube. You can do searches on anything, and you can find a lot of information about it. But it's all the same because nobody knows anything more. Anyways, I wanted to show about why isotope analysis is something that is, important. Okay, so now we're going to look at writing atomic symbols. So I showed you guys how to write atomic symbols, so I kind of jumped ahead in your slides, so hopefully this is a little easier. Mass number always goes on top. That's the proton plus the neutron number, the total. And the atomic number is the protons on the bottom. This is helium. Why is this helium? Because helium has 2 neutrons. It has 2 protons, so that makes the mass number 4. And remember that address I was telling you about? It's 2. So it is helium. Nitrogen has an atomic number of 7. Fluorine has an atomic number of 9. Sodium has an atomic number of 11. And argon has an atomic number of 18. And these are all the masses. So if you subtract these, this will tell you how many neutrons that element has. Okay, so let's take a look at an example. An important isotope. So there's a key word right there. We're dealing with an isotope. So this isotope, that mass, will most likely not match the periodic table mass that is shown. And we're going to explain why on this slide. Has an isotope of uranium has 92 protons and 143 neutrons. Write the symbol with the atomic and mass numbers. So the first thing you do is you make sure you understand what the chemical symbol is for uranium, and it's U. So let's pretend I wrote a U. The next thing is the mass always goes on top. So how would I get the mass? Or actually, if you want to make it easier yourself, write 92 because the number's just given to you. You could look it up on a periodic table or because it specifically states it here. So you write 92 on the bottom. So larger number on top, lower number on the bottom. Now, how do we get the mass number? We can't look at a periodic table because this is an isotope, so it's not going to match what's showing up here. We add this number, and that gives us 235. So here we have 235. So if we were dealing with this number would be gone. It would look similar to the carbon that I showed you guys like that. That's normally how it is. Or it would say here something like uranium 235. That's how you know that you're dealing with something that's an isotope and not something that is on the periodic table. So now why does this number not match this number? Well, that's because the mass number on the periodic table is the average of the isotopes. And the isotope that is in the greatest portion dominates the mass number that is shown on the periodic table. If that doesn't make sense, it will because we're going to do some nice fun algebra and math on this. So the average atomic mass is weighted average of the different isotopes. So for instance, if we go back and we look at these isotopes, if you look on a periodic table, the average is 12.01. Why? Because that means that this is the greater in abundance of all 3 of the isotopes. So it's the weighted mass number that shows on the periodic table is going to match this one because it's more. There's more of it than there is this one, and there is this one. But the 0.01 is because of these. So that tells me there's almost trace amounts of these, and it dominates by this one. All right, so let's get started so I can show you. So how do we know how to do this? How do we know how to look at the mass number of periodic table and know the percentage? Here's an example of a weighted average. So how do they take a weighted average and find the mass? Well, we're going to use an example of poker chips. Let's say you have a big pile of poker chips and you want to know, you want to take the average of these poker chips. meaning that you have two different types of poker chips. You have 10% of the chips are worth $1, and 90% of the chips are worth $2. But you want to know the average value between these two, and that's based on how many you have. So here is the general formula, and you're going to use this general formula when we start working with isotopes. But here's a perfect example of how to do it with chips. You take the value of A, and we're going to say A is the dollar, and then you're going to do a parentheses, plus sign, parentheses, and the same thing. You grab the $2 and write the $2. Now we're going to look at the percentage. There are 10% of $1 chips. So we're going to write 10% here. However, we're going to do it in decimal form. How do you do that? Well, we're going to take 90% and we're going to write this one, but it has to be in decimal form. So how do you do that? Most of the time that chemistry students struggle in chemistry, it's because of algebra. It actually has nothing to do with chemistry. The subject is chemistry, but it's not chemistry. Students have a hard time remembering algebra. That's I would say 80 to 90% of the time, if they're making an effort with the content, it's the algebra. So how did I get this? Well, very easy. When you have to do a percent, the last step is to multiply by 100, and that gets you this. Well, we don't want it in percent form. We want to keep it in decimal form, so we have to work backwards. So instead of leaving it in percent form, we divide it by 100, and that gives us decimal form. So that's how this one is this way, and that's how this one is this way. Now we multiply these together, and add it, and it tells me that the average value of these pile of chips is $1.9. We're going to leave it at that because of the fact of sig figs, and this is how your book wants to show. So I'm going to just say $1.9. Okay, so now I'm going to use that information and transfer it into chemistry. We're going to do the same exact thing. Sig figs still apply, by the way, okay? So we have carbons. Remember I was talking about carbon? Carbon atoms exist primarily as two isotopes. Yes, there is another isotope, but it only right now wants to focus on these two. So we're going to pretend I never showed you the last one. What is the average atomic mass for carbon? This is how we get the average atomic masses on the periodic table. So what you see on the periodic table is an average of the isotopes for some of these atoms. So we take that same format that is here in blue, and we're going to pull it. So we take, remember, U stands for atomic mass unit, which is how we look at the weight. That's the units that go with this. And here we have 12, and it's giving us all these sig figs. Now here's the percentage of the makeup for these two carbons. Wow, it's just completely kicked out carbon 14, which I find is interesting, but okay. How did we get this number? Same thing. We divided it by 100 and it put it in the decimal form just like I did here. Okay, now we do a plus sign, gives us all these sig fig numbers, put that here. And then it's telling us that we have, the majority is 98.93% and carbon 13 is 1.107%. Divide that by 100 and here is our amount. So now we multiply this together, we multiply this together, follow the sig fig rules, and in the end of all of this, we end up with 12.01 U. Here's a unit, here's a unit. That's where that unit shows up to. I'm going to show you more examples. This isn't the only one. All right, so here's another one from my other slides. Magnesium has 3 occurring isotopes, and the atomic mass is 24.31 AMU. I'm staring at this because this is so large, and it wasn't large like that when I was looking at it before. So the atomic mass on the periodic table is 24.31. That means that majority of it matches the isotope that is close in the mass to it. So this makeup is 78.70% with a mass of 24. Magnesium 25 is made up of 10.13%, and magnesium 26 is made up of 11.17%. So that's where, when you add these averages together, and we do it in the form of this, here, this form, then you can see by adding it together, this is the average weighted mass. So that's where you see when this is on here, it's taking the average of all the isotopes, but the value will be closest to the one that is greater in percentage than the others. So here it says table 4.7. This is not in your book. I meant to take that off. But this is in another of my courses I cover. So here is magnesium 24, how you write it out. Here it is an atomic symbol or chemical atomic symbol. We'll see with that. Magnesium 25, magnesium 26. Number of protons are the same. Number of electrons are the same. But the mass number is different. Why? Because the number of neutrons is different. The mass of isotope, so this is the mass for this one, this is the mass for this one, this is the mass, and the percent abundance of how many. Okay, so calculating atomic mass. We use the experimental percent abundance of each isotope of the element and then divide it by 100 to get in decimal form. Multiply the percent abundant by the atomic mass of that isotope. And then you sum the total of all that together. And that's pretty much what you see here. And sometimes you will get 3 or 4 and you have to do the same thing and then add it at the end. So let's take a look at a problem. A large sample of naturally occurring chlorine atoms consists of 75.76% of chlorine 35 and 24.24% of chlorine 17. The chlorine 35 isotope's mass is 34.97 AMU, and the chlorine 37 isotope's mass is 3697. So we have enough now to figure out what the average weighted mass of this isotope is, of the total of the isotopes. So I'm going to cheat and just show you how to do this. So we calculate, here it is, the formula, that's here. So we take the isotope mass, times it by the percent. I did it by dividing 100, so you can see it looks nicer here. And then how many we have gets us our average weighted mass. So here is the mass of chlorine 35, and then the percent abundance divided by 100, plus the mass of chlorine 37, and the percent abundance divided by 100. And that will give us the average atomic mass. So we're going to skip ahead. And I pulled everything out, and you can see how I did it. Here is the bottom with everything calculated. Add these together, and sig figs still apply on all of this stuff. The average atomic mass is 35.45 AMU. You can see the units stayed with it the whole time. All right, so here is the atomic mass of some elements. So this is telling you which is the most abundant, the average weighted, and the isotopes for some elements. All right, so let's do one more. I think this is. Lithium consists of 2 naturally occurring isotopes, lithium-6 and lithium-7. Use the periodic table to predict which isotope is more prevalent one. I'm not going to show periodic table. I'm just going to tell you that the mass that shows on periodic table is 6.941. So which one is the more prevalent one? Well, it's closer to 7. So that means that the isotope lithium-7 is more prevalent, which means it's more in abundance than the lithium-6, because the average atomic mass is closer to 7 than it is to 6. Oh, we have one more problem. Gallium is an element found in lasers used in compact disc players. In a sample of gallium, there is 60.10% of gallium-69, and it has an atomic mass. And then we have 39.90% of gallium-71. What is the atomic mass? So it's the same thing. We pull everything out. We follow the same steps. They do not change no matter how many isotopes you have. You just have to follow the sig figs, and that's where some people get confused. Carry the units as well. And in this case, the answer is 69.72 AMU. So if we look at it, we expect this number to be, there's 60% of gallium-69 and almost 40% of gallium-71. This number is closer to 70, but it's still 69. So that would tell me that this one is higher in abundance than this one without even looking at the percentage. Okay, so summary of elements and atoms and elements. Protons determine the identity of atoms. Atomic number is protons. Remember, that's the address on the periodic table. Mass number is protons plus neutrons. Isotopes, same number of protons, different amount of neutrons. The periodic table is the atomic number and the average atomic mass.